There are moments when astronomy seems to move forward in predictable steps, slowly accumulating data and patiently fitting theories together. And then, from time to time, an object appears that interrupts this rhythm. Not because it destroys what we already know, but because it begins to reveal layers of complexity faster than we can explain them. That is exactly what happened when the interstellar visitor 3I Atlas entered our field of view. In a short time, it stopped being just another curious discovery and began to occupy a rare space, the meeting point between scientific discovery, intense academic debate, and growing public speculation. A messenger from another stellar system that crossed the solar system, leaving behind a trail of data that, taken individually, seem ordinary, but together form a surprisingly difficult puzzle to assemble. It is as if each observation were a discrete piece. Chemistry, dynamics, trajectory, brightness, activity, apparently simple when analyzed alone. However, when placed side by side, these pieces stop forming the expected image and begin to reveal something far more complex than any standard model can comfortably explain. This is not a single gigantic mystery, but several small deviations that insist on pointing in the same direction. Something here does not follow the typical script. This type of encounter is already rare by definition. Interstellar objects do not belong to our planetary system. They are fragments expelled from other stellar systems during the violent stages of planet formation, when gravitational interactions between gas giants and debris disks launch trillions of bodies into interstellar space. Most of these fragments will wander the galaxy for millions or billions of years without ever encountering another star. Only a tiny fraction will cross, by pure gravitational chance, the region dominated by the Sun. We have detected only 3 so far, and the third ended up becoming the most intriguing of all. What makes this even more fascinating is that these visitors function as cosmic time capsules. Unlike comets from our own system, which have endured billions of years of solar influence, collisions, and periodic heating, an interstellar object preserves records of a completely different environment. It carries the chemical, thermal, and dynamical signature of an unknown stellar system. Every measurement, every spectrum, every light curve is, quite literally, an indirect sample of another region of the galaxy. And it was precisely one of these measurements that began to transform 3I Atlas into a special case. Everything started with a chemical discovery that immediately caught the attention of the scientific community. Astronomers detected pure nickel vapor in the object's coma, with no sign of iron. This may sound like a technical detail, but within planetary science it is deeply strange. In decades of observations, iron and nickel always appear together in comets. They are born together in ancient stars, remain together in metallic minerals, and are released together when a comet heats up. In 3I Atlas, only nickel was present. Iron simply did not appear, not even at the level of instrumental noise, where we usually find residual traces of almost everything. The team responsible used the UVS instrument on the Very Large Telescope to analyze the object's spectrum at nearly 4 astronomical units from the Sun. The nickel spectral lines were clear, consistent, and passed rigorous checks. Detailed calibration, background subtraction, comparison with atomic databases, and independent repetition by different teams. This type of cross-verification is essential because extraordinary discoveries require an extraordinary level of verification. And even after all the checks, the result remained the same. There was nickel, and there was no iron. This separation caught the attention even of scientists accustomed to unusual results. Avi Loeb pointed out that, on Earth, pure nickel without iron is typical of highly specific industrial processes. In nature, these metals rarely separate in this way. He did not claim this proves technology, but he raised an uncomfortable and scientifically legitimate question. What natural process could produce this chemical signature? A plausible hypothesis quickly emerged. Nickel carbonyl, a volatile compound that can form when carbon monoxide interacts with nickel-rich surfaces. This compound evaporates at relatively low temperatures and decomposes under solar radiation, releasing atomic nickel. That would explain why nickel appears first, while iron remains trapped in more resistant minerals. It is an elegant explanation, consistent with known physics, but unprecedented in comets. And even when a plausible explanation appears, the fact that we have never seen anything similar keeps the mystery alive. While chemistry raised questions, the observation history began to reveal something equally intriguing. Before being officially discovered, the object had already been recorded by automated survey telescopes. Archived data showed it was visible weeks before the official announcement. It was an amateur astronomer working from home who helped track these older images and extend the observation timeline. This detail reveals something fascinating about modern science. Today, astronomy is a global collaboration between giant telescopes and ordinary people with access to public data. These data revealed something unexpected. 3I Atlas was already active at 6.4 astronomical units from the Sun, beyond Jupiter's orbit. Normally, comets remain dormant at that distance. Solar energy is too weak to heat water ice. Here, gas release had already begun. The TESS satellite, designed to hunt exoplanets, captured the object slowly shining in the background of the sky. The light curve showed persistent and consistent activity. This indicated the presence of extremely volatile ices, such as carbon monoxide and carbon dioxide, capable of sublimating far from the Sun. In other words, this visitor began to wake up much earlier than expected. As the object approached, the rate of material release increased dramatically. Estimates indicated it was releasing water at about 88 pounds per second, at nearly 3 astronomical units from the Sun. This activity persisted for months, suggesting a massive body rich in volatiles. Models indicated that 3I Atlas may be about 1,000 times more massive than Oumuamua. Objects of this size should enter the solar system only once every 10,000 years. Yet there it was, crossing our cosmic neighborhood as if it were just another passing visitor. When the James Webb Space Telescope observed the object in the infrared, another surprise emerged. The ratio of carbon dioxide to water was 8:1. This is extremely unusual in cometary chemistry. No single explanation managed to accommodate the data. The team presented 3 possible scenarios: formation in extremely cold regions, prolonged chemical processing, or a combination of both, and chose none as definitive. The coma's color also changed rapidly, becoming redder night after night. This change suggested the release of complex organic compounds or material processed by billions of years of cosmic radiation. This means that what we are observing may not represent the object's original composition, but a surface deeply transformed by ages in interstellar space, an irradiated crust that holds clues to a past impossible to fully reconstruct. The orbital trajectory added another curious detail. The object's inclination relative to the ecliptic was extremely low. This allowed relatively close approaches to the inner planets. Some calculations estimated that the probability of this geometry would be tiny. Critics reminded us that probabilities calculated after the event prove nothing extraordinary, and that is true, but the debate gained momentum because each new detail seemed unlikely when considered in isolation. At perihelion, the spectacle reached its peak. The object displayed giant jets emerging from the nucleus, forming plumes stretching millions of miles. The activity rivaled the most dramatic cometary outbursts ever recorded. It was the moment when the visitor showed all its accumulated energy after billions of years in interstellar cold. Solar radiation released chemistry stored for ages. And then came weeks of institutional silence. In this informational vacuum, speculation exploded on social media, mixing legitimate science, public curiosity, and conspiracy theories. When NASA finally spoke, the message was direct. The object is a comet. It looks and behaves like a comet, and all the evidence points in that direction. Even so, the scientific papers themselves admit uncertainties. No single model explains all the data simultaneously. Final observations brought yet another surprise. Methanol levels 4 times higher than those of typical comets, an essential ingredient in the chemistry that leads to complex organic molecules. Another piece of the puzzle. Another clue that reinforces the feeling that we are only beginning to understand the diversity of interstellar objects. Today we know the object is billions of years old, crossed interstellar space for ages, and passed near dozens of stars before arriving here. Its surface was bombarded by cosmic rays for billions of years, profoundly altering its chemistry. And now it is leaving. After December 2025, our observation window closes forever. The images and data will be archived, analyzed, and reanalyzed for decades. Perhaps new missions and new telescopes will find similar visitors in the future. Perhaps we will discover that 3I Atlas is only the first example of an entire population of objects we still do not fully understand. If you made it this far, take a moment to like the video, subscribe to the channel, and comment on what you think we are really seeing: an unusual comet, or the beginning of a new era in interstellar exploration. The visitor continues its journey toward deep space, and the answers remain just beyond our reach.